Hey there, how's it going everybody? In this video, we're going to set up an IPSec VPN between two Juniper SRXs using PKI certificates for authentication. We're also going to use IKE Proxy Identity, also known as traffic selectors, to have multiple IPSec SAs spawn from our IKE SA. Alright, let's look at the topology. As you can see, the topology we're working with is fairly straightforward. Both SRXs are connected to the internet via the black links and can ping each other's internet IP. The two dashed blue links represent the IPSec VPN that we're going to configure, each one being a separate IPSec SA. We're going to do them as route-based, not policy-based, so we'll have a tunnel interface associated with each SA. ST0.21 and ST0.121. Also, we'll use IKE v2 and bring up OSPF across the tunnels so we can ping between the two loopback IPs of the SRXs, 10.0.0.20 and .21. This will verify that the IPSec VPN is up and routing. Let's talk about what we'll be using for authentication. Public Key Infrastructure, or PKI, certificates. A certificate is essentially an identification document. It's analogous to a government-issued photo ID. Let's think of a real-world example, say renting a car, where you must show your ID. The business renting you the car wants to be sure they know who you are and have some identifying information of you on file, such as your address. In the case of using a credit card, they want to be confident you're the owner of that credit card. Now, in some places it's required by law that they check your ID, but that's not the point of the analogy. The point is, why do they trust your ID? The answer is that they trust the government, and they know what a government-issued ID looks like. So if the ID you present them looks government-issued, they trust it and the information on it. They'll also check the expiration date to make sure it's still valid, and they'll check the photo to make sure you're the owner of this ID. Notice how their trust in the government doesn't extend to the ID until they recognize it as government issued, and that the trust doesn't extend to you until they verify you're the owner of the ID by looking at the photo on it. Then they accept the ID and trust that the information on it describes you, like the address or date of birth. This is how certificates work. However, it's certificate authorities, or CAs, who issue the certificates. If the party you present your certificate to trusts that CA, then they'll trust your certificate, assuming it's not expired. Once you prove you own the certificate, then they'll also trust you. So let's go over the birth of a certificate so we understand how they get issued, and this will help us better understand what's happening under the hood. The birth of a certificate begins with the generation of a key pair, and in this example, we'll use SRX0. SRX0 is going to generate an RSA 2048-bit key pair. Now, it's called a key pair because they have a mathematical relationship where whatever you encrypt with one key can only be decrypted with the other key, and vice versa. This is called asymmetric encryption. That stands in contrast with symmetric encryption that IKE and IPSec use. Talking about IKE, you have a Diffie-Hellman derived key. Both sides use the same key to encrypt and decrypt the traffic. That is considered symmetric encryption and symmetric keying, since both sides are using the same key. IPSec is considered symmetric encryption but asymmetric keys, because the same key used to encrypt is the same key used to decrypt. However, both sides are using different keys to encrypt their traffic, which is why both sides have to have both keys, one for encryption, one for decryption. What we're talking about here with certificates is asymmetric encryption. Whatever you encrypt with one of the keys of the pair, you must use the other key of the pair to decrypt. Now, this special relationship is the foundation for signatures. What it allows us to do is to keep one of these keys private and secret from the rest of the world, and then publish the other key publicly to the rest of the world. Now we can run a hash of a file that we want to endorse, And then we can encrypt the hash with our secret key, our private key. When we affix that encrypted hash onto the file and it goes out to whatever party wants to verify it was signed, they can use the public key, decrypt the signature, see that the hash inside matches the hash of the file, and know that we endorsed that file and that file hasn't changed since we endorsed it. And they know we endorsed it, again, because they used the public key to decrypt the encrypted hash, and what they found inside was an accurate hash of the file. The only way that could have happened is if we, with the corresponding private secret key, encrypted that hash. So that is the foundation of signatures. So what we're going to do is we're going to use the certificate not only as an identifying document, but as a vehicle to get our public key out to whom we want to have it. And so the certificate is seen as a publicly accessible document. So after we generate the key pair, in order to get the certificate, we need to generate a certificate signing request that's going to go to the certificate authority and then be endorsed by the certificate authority. So be signed by the certificate authority. So first, we put our public key in the certificate signing request. Next, we want to add our identifying information. This is analogous with the identifying information that we talked about on the government issued photo ID, where we had address, height, weight, hair color, eye color, age, things of that nature. The subject is a list of strings, distinguished names is what they're called, that describe identity factors of us. So the most important one, and the one that has to be included, is the common name, which is normally a host name or a fully qualified domain name. Other optional distinguished names that go in the subject are the organization, the organizational unit, the locality, which is normally used for city, the state, and the country. There are more, but those are the main ones. The other thing we're going to put in the certificate signing request is something called the subject alternative name. So the subject alternative name is a list of DNS names and IP addresses of hosts that are allowed to use this same cert. This is more of a feature when you have a cluster of servers and you need that cluster because they're providing up the same web page. You need that cluster to share the same cert so that it shares the same identity to the rest of the world. And so that's where the subject alternative name, the SAN, comes in. It lists the DNS names and or the IP addresses of all the servers that are sharing the same cert because they're sharing the same identity. The next thing we need to do is add our signature. Now this signature is not going to survive and be published with the certificate. The signature on the CSR is simply to demonstrate to the certificate authority that we endorse, we signed this CSR, meaning it came from us and was not tampered with en route. So we're going to run a hash of the CSR. We're going to encrypt it with our private secret key, and then we're going to put that encrypted hash on the CSR, and that's considered our signature. And since our public key is on the CSR, the certificate authority is going to be able to use that public key to decrypt the signature, review the hash, and verify that it matches the hash of the CSR and that it wasn't tampered with and in fact endorsed by us. And the final thing that goes on the CSR is just a hash, a plain text hash of the entire file, including our signature, and that's called the fingerprint or the thumbprint. Next, we get the CSR over to the CA. There's multiple ways that you can get the CSR over to the CA. We're not going to talk about those right now. We'll cover that later during the CLI configuration. Once the CSR gets to the certificate authority, its job is to now review the information and add or remove some additional information, possibly even tweak some information, and then it's going to sign or endorse and produce the certificate that's going to be available for third parties. So it maintains the public key that we had in our CSR. It reviews the subject, the SAN, and if it concurs with that information, then it allows it to remain. And then it's going to add something called the validity period. It's going to be the start date and the end date that the certificate is valid for. So the certificate won't be trusted before this date and won't be trusted after another date. The another thing it's going to add is a serial number, which is certificate authority specific. Every certificate produced by a certificate authority gets a serial number. And so it's going to just stamp a serial number on the certificate. The third thing it's going to add is the certificate revocation list URL. So one of the problems with certificates is that we're having the certificate authority endorse a certificate, sign a certificate, and say, here's an identity document that can be trusted if you trust me. But what if the private secret key gets compromised? The person who the certificate belongs to needs a mechanism, and the certificate authority needs a mechanism to revoke a certificate in case the certificate can no longer be trusted because the private secret key was lost or compromised. So the certificate authority is going to maintain a certificate revocation list, which is simply a file, and in the file is a list of serial numbers. And the idea is if the serial number of the cert that you're verifying is listed on the CRL, you shouldn't trust it. But we need whoever's verifying the certificate to know the URL of where that CRL can be found. So that's what we're talking about here. So the CRL does not get put on the certificate. The URL to the CRL gets put on the certificate. So when the certificate's being verified, the verifier can go to the URL, download the CRL, search the CRL for the serial number of the certificate, make sure it's not listed, then it can proceed with verifying the certificate. The next thing the CA is going to add is its own signature, right? It's going to run a hash of the certificate. It's going to encrypt that hash with its own private secret key. And then it's going to put that encrypted hash on the certificate. That way the public can see and verify that this certificate was in fact endorsed by the CA. The final thing that will get added is the fingerprint or the thumbprint, which is simply an unencrypted hash of the entire file, including the CA signature. Now, right here, you should be asking yourself, wait a minute. If we're verifying this certificate for SRX0, how do we know to trust the certificate authority? And where do we get the certificate authority's public key to decrypt the CA signature and verify that it is his signature? So the certificate authority has its own certificate. So just like all these entities or routers are going to get certificates issued by the certificate authority, the certificate authority itself has its own key pair, and its public key is in its certificate, and its private key is kept a secret. So then your next question should be, okay, well then who signs the certificate authority's certificate? And the answer is the CA signs its own certificate. And for that reason, the CA certificate has to be administratively configured and trusted. You actually have to load the CA certificate, in this case, onto our router and tell our router to trust that certificate. That way, we have the public key, we have the certificate and the public key that's on it, and we trust it. Now we can use that to look at SRX1's certificate, for instance, decrypt the CDA's signature, and verify that SRX1 certificate is valid. So now let's quickly look at how the certificate authentication fits into the IKE exchange. And if you need to review IKE and IPSec concepts, I have covered that in a previous video, and I have a link to it down in the description box below with the timestamp, so you quickly jump back and see why we use IPSec VPNs and how IKE and IPSec interoperate. For this part, we're just looking at how the certificate authentication fits into the IKE process that we already know. So here we have SRX0 and SRX1. In this case, SRX0 is going to be the initiator. He's going to be the first one to get off his init packet. So he sends the init packet unencrypted across, in this case, the internet, and it's going to have the IKE proposals, the public part of his Diffie-Hellman, and the one-time use random number called the nonce. SRX1 is going to receive that and is going to reply with its own unencrypted init packet with its IKE proposals, the public part of its Diffie-Hellman, its nonce, and since SRX1 knows that SRX0 wants to do certificate-based authentication, and he knows he himself wants to do a certificate-based authentication, he's going to send a certificate request in this second init packet, replying to SRX0. So then SRX0, at this point, once he gets the init packet from SRX1, has everything he needs to create the encrypted IKE tunnel. And if everything succeeds with the next two packets, which are the two authentication packets, then this IKE tunnel will stay up and continue, and the IPSec tunnel will be spawned. If anything fails with either of these two auth packets, then this IKE tunnel will be torn down. So in this auth packet that SRX0 sends, there's going to be the authentication piece. We're going to get back to that in a second. Then there's going to be his IKE ID, his certificate. He's going to make a certificate request of SRX1, and then he's going to have his IPSec proposals, and then his IKE Proxy Identity / traffic selector for the IPSec SA. So what the proxy identity / traffic selector is a remnant from policy-based VPNs where we had to define, okay, we want to do a VPN off this interface, and any traffic from this IP or network going to this IP or network and of this IP protocol, go ahead and encrypt it if it's egressing this physical interface. That's how policy-based VPNs work. And these traffic selectors were critical and fundamental to how they worked. With route-based VPNs, we encrypt anything that the routing engine sends to the bound tunnel interface gets encrypted by the IPSec SA outbound. Anything we receive on that IPSec SA inbound gets decrypted and ingressed to the corresponding tunnel interface. So we don't really care, particularly we don't care in the case of a single IPSec SA what the traffic selector is. And if you don't set it, then by default it's from anywhere to anywhere, any protocol. But it has no bearing because it's ignored essentially. The only way that it matters is that both sides have to agree what these traffic selectors are for a given IPSec SA, and if you don't set them, then both sides agree that they're from 0 to 0, any protocol. So the way that we use this when we're doing multiple IPSec SAs is that it's a way to color or uniquely identify one IPSec SA from another. And so you're going to see when we get to the CLI, since we're going to be doing two child IPSec SAs, each one is going to have its own IKE proxy identity, its own traffic selectors, and both sides have to agree what the traffic selectors are for each child IPSec SA. But what they are doesn't matter so long as both sides agree what they are and that they're different from each other, from one IPSec SA to the other. Now going back to the auth block or the auth piece at the very beginning of this auth packet. So what this is similar to how the pre-shared key worked, where we're going to take both nonces and the local IKE ID. Now we don't have a pre-shared key, so that's left out, right? But we take both nonces and the IKE ID, and we're going to send it through that hash and get a hash result. Then we're going to take that hash result, and SRX0 is going to use its private secret key that corresponds to his certificate, and he's going to encrypt or sign that hash, and that's what's going to become the auth block. Now SRX1 is going to go through the certificate verification process for the certificate he just received from SRX0. Once he determines that he trusts that cert, then he's going to take the public key off that cert for SRX0, and he's going to use it to decrypt the auth block. And inside, he expects to find a hash. And then SRX1 is going to run a hash on the both nonces and the IKE ID. And if the hashes match, then he knows for certain that SRX0 has the private secret key that corresponds to the cert that he just received. So now he can trust the cert, and now he can trust SRX0. Once that happens, SRX1 has authenticated SRX0, and so SRX1 sends his auth packet towards SRX0. That's packet number 4. And SRX0 does all the same stuff we just talked about, but against SRX1. So SRX1 sends his auth block, his IKE ID, his cert, his IPSec proposals, and his traffic selectors. And then SRX0 gathers that information and not only verifies the IPSec proposals and the traffic selectors match for the corresponding child SA, he also verifies the cert that SRX1 sent, And then if he verifies it successfully, he takes the public key off, decrypts the auth block, and verifies the signature. Verifies SRX1 has the corresponding private secret key. So what the verification of the certificate looks like, very briefly, is it's a 4-step process: validity, trust, ownership, and identity. So the first thing that both sides are looking at when they look at the certificate they received is the certificate active but not expired? So that means, is the date, does it fall between the start and end date that's listed on the cert? Then the next thing they look at is the certificate signed by a CA that I trust? And if it is signed by the CA that they trust, then they decrypt that signature, right? They verify that CA signature on that cert and make sure the cert hash matches the encrypted hash that's in the CA signature. Make sure the cert hasn't been tampered with since it was endorsed, since it was signed. If that checks out good, then it goes to the URL that has the CRL for that cert, for that CA, and it downloads the CRL and makes sure that the cert's serial number is not listed on the CRL. If that is good and it's not listed, then it trusts the cert, and it goes on to the next step, which is ownership. And this is where he asks himself, does the entity who presented this cert have a matching private key? So this is where they trust the cert, so each side takes the public key off the cert, and they decrypt that auth block, or that auth piece I was talking about. Inside, they find the hash of the two nonces in the IKE identity, and then they run their own hash on the two nonces and IKE identity, and the hashes match. Then they know the peer, the IPSec VPN peer who sent the cert, also has the corresponding secret key, and therefore is the owner of the cert. And then the fourth step is the identity piece. So this is where, now that we trust the cert and we trust that the person who sent it to us owns the cert, now we're going to look at the cert and ask ourselves, are you someone that we're configured to do an IPSec VPN with, right? So it'll look at the subject name, and it'll look at the common name in the subject name and say, okay, are you the host name or the FQDN who I'm configured to do a VPN with? Or maybe it'll look at the organizational unit. There's a bunch of things it can look at on the cert to determine if it wants to do a VPN with that peer. All right, without further ado, let's get to configuring the CLI. I just wanted to show you the topology again really quickly so we could remember what the loopback IPs were, remember what the topology looked like with our connection to the internet and the two secure tunnels. So this is what we're going to be referencing, and we're going to start configuring SRX0. So here we are on SRX0, and the first thing we're going to do is we're just going to verify that we are in flow mode. Remember, SRXs by default are in flow mode, and it needs to be in flow mode to do IPSec VPNs. So we're in flow mode. Now let's get our bearings. All right. Looks like we have our internet interface like we'd expect, our loopback, and this is just the management interface I'm using for the lab. Let's take a look at our routes. Okay, so yep, this is what we'd expect. 10.0.0.20 on our loopback interface. Here's our internet connection with our internet IP and our subnet that's connecting to the internet. Out interface 000. And here's our default route, which is going to the ISP, static default route. All right, let's also quickly check our security zone configuration. On SRXs in flow mode, you have to have an interface and a security zone for it to work. So if you look at here, we have our internet security zone with our internet interface, and you can see that we are allowing ping and IKE. Now that's going to be important, right? Because if we're doing IPSec VPNs, we have to permit IKE. And if you permit IKE, it'll also permit the child IPSec. All right, and then here's our corporate zone, and with our loopback internet. And then the last thing we need to check is our security policies. All right, so here's our configured security policy for the corporate zone, which is going to allow traffic from corporate to corporate. So that's what's going to allow traffic from our loopback interface to our tunnel interfaces once we get them configured. And it's going to allow any source, any destination, any protocol, and then it's going to permit it. So that's what we'd expect. That's exactly what we want. All right, that's good. So the first thing we need to do is make sure that our date is set correctly, because whenever you're dealing with certificates, we need to make sure that we have an accurate date. So let's do a show system uptime. You can see we've only been up for 10 minutes, and it's saying it's November 2nd, 2020, and the GMT or UTC time is 1817, which is accurate. So we're going to leave that. The next thing we need to do is configure DNS, because the URL for the CRL is going to be a URL that's going to need to be resolved. So the DNS server for the lab, which is just a completely made up IP address that I have here in the lab, is this right here, 35.15.173.8, and I can ping it. So we're going to need to go ahead and set that. Set system name server. And let's get that configured as our DNS. So in the real world, you would need to configure DNS if you're going to be doing revocation checks. Otherwise, you need to disable the revocation check. All right, the next thing we need to do is we need to create, we're going to start loading our PKIs, our certificates. And the first one we're going to load is the CA certificate. And you need to create a container for the CA certificate to go in. And that container is essentially called the CA profile. So we need to say set security PKI CA profile. We're just going to name it something obvious like CA prof. And then you need to give it an identity. And it doesn't really matter what this identity is, so we're just going to name it CA cert. That's all we have to set. There's a ton of settings under this profile that we could mess with. Namely, we could turn on and off the revocation check. We could make it use CRL. It's gonna use CRL by default. That's what we want. You can also set the routing instance or source address. We're not gonna mess with any of that. So now we have our CA profile configured, and we're gonna go ahead and commit that. All right, so now that that's committed, we can begin the next steps. So the next thing I need to do is I need to copy the CA certificate. So I have a CA for this lab, and if you guys are interested in learning how to run a lab CA, then just comment in the down below this video, and maybe I can do another video that shows you how to set up your own lab CA, but that's outside the scope of this video. Just know that I have my own CA, and I need to get that CA cert onto this router, or this SRX, the first step. So we're going to say file copy, and it's an HTTP location. It's just this lab IP address right here, and the file is called CA cert. And we're going to copy it to var temp PKI. I just made an empty directory called PKI. That's where we're going to copy it to. All right, so let's do let's just quickly look in this directory. So it's just an empty directory. We copy the CA cert to it. It's not particularly interesting if you just try to look at it. It's in base 64. So if you guys are familiar with hexadecimal, which is base 16, right? You have 0 through 9, A through F. So you can represent values of 0 through 15 in a single digit. Base 64 uses the entire alphabet, all capital letters. That's 26. The entire alphabet, all lowercase letters. That's another 26. Now you're up to 52. Then it uses numbers 0 through 9, that's 10, so now you're up to 62, and then it uses the plus sign and the forward slash. The plus sign and the forward slash. So that equals 64. So basically each one of these digits represents a value between 0 and 63. So this doesn't look like a lot, but this is actually like a 1 kilobyte file. So it's a pretty decent size. All right, so this is our certificate. Now let's get it loaded. Right now it's just sitting in our file system. We need to get loaded into the into that CA profile. That's basically a container that we created earlier. So request security PKI CA certificate load, and we're going to load it into the CA profile we created, which is called CA profile. And then we're pulling the file from file name var temp PKI CA CRT. Now right here, this is that fingerprint / thumbprint I talked about, where this is just the unencrypted hash. And here's where you would check and say, wait a minute, does this thumbprint or fingerprint match what I need it to match? And since I'm running the CA, I can tell you it does. This is the correct thumbprint. So we can go ahead and load this. So we're going to say yes. Now when this loads, you see how it says loaded successfully? So there's a couple of checks done here. So one of the first checks it's done is it actually makes sure the certificate is valid. So let's just go ahead and look at this real quick. So here's our certificate in like human readable form. So the certificate identifier is just CA Prof because that's the container we put it in. Here's the serial number I talked about, where any certificate that a CA publishes has a serial number on it, a unique serial number. There it is. Here you can see that the issuer and the subject are the same, right? Because we talked about how the CA signs its own certificate. So this is the signer, and this is who the certificate is for, and you can see it's the same person. The common name that's configured on this is just ca.node9.lab, a completely made up URL that's not real. And you can see here I went ahead and put in some information into the subject line. Remember I told you about the distinguished names that make up a string and a list, and that's the subject. So this, fake organization Node9 has a organizational unit called Lab. It's in the US. It's in Hawaii. I've always wanted to live there, the island of Oahu. And here you can see the listed strings right here. Here's that subject alternative name I talked about, and you can see that it's using an FQDN, but it doesn't have any email or IP addresses listed. Here's that validity period I talked about. This cert is not good before November 1st, 2020, and it's not good after November 1st, 2030. So since today is November 2nd, this cert is good, Here's the public key that we're going to be using. We're going to be pulling off this certificate to decrypt and verifying other certificates. Here's the SHA-256 hashing algorithm that's going to be used with this certificate, with this key. Here's the CRL location. So this is why we need to configure DNS, because it's going to use this URL to pull down the CRL and check certs to make sure they're not revoked. And then here's that fingerprint that we just verified and said, yep, that's the fingerprint it should be. So let's do another command here. Let's do show security CRL detail. So because this CA cert had a CRL listed, and part of the job of the Juniper SRX is to verify that this cert is also not revoked, it actually pulled down this CRL, and here it is. So this CRL is in the same container that the CA cert is in, the CA profile container. And you can see here the issuer of the CRL is this right here. Now, one thing you need to be aware of is the CRL is also signed. So that's what's really cool about CRLs, is that you can't have bad actors like making fake CRLs, because the CRL is also signed. You can't really see it in this output, but it is. So if somebody publishes a bunk CRL and tries to trick you and say, oh no, there's no certs that are revoked, you won't believe it because it won't be signed by the CA. So you can see the effective date of the CRL is essentially a month. That's pretty normal. They normally publish a new CRL every month. And you can see there's already some revoked certs on here. I just did that so you can see what it looks like. So I just made some certs and then revoked them just so you can see what they look like. So what it's going to do is when it's starting to check this CA cert, this serial number up here, if this serial number was listed in this list, then it wouldn't trust it. But since it's not listed, it says, okay, this CA cert must be good, not revoked. And when we start to check the SRX certs, those serial numbers must not be listed here, otherwise they won't be trusted. All right, so now we have our CA cert. It's loaded, it's trusted by the box, everything's happy. When you load it, it says that it's loaded successfully. If you're, if you're not sure and you kind of want to check again, you can always say request security PKI CA certificate verify. Oop. And you have to say what you're trying to verify. And it basically just re-verifies the cert that's in the container you specify. So if something had changed, let's say 10 years passed and the CA cert's now expired, running this command will tell you something's wrong with the cert, that it's either expired or that it got revoked, whatever. All right, so let's go ahead and generate our key pair. So we need to say request security PKI generate key pair. And now we need to give this a container ID. It's called a certificate ID. So this is going to be a container that's going to hold the key pair. It's going to hold the certificate signing request. And then once we get our certificate, it's going to hold the certificate. It's going to hold all three things. And the reason why it needs a container is because it needs to relate those three things together, right? When it gets a certificate, it needs to know what key pair to use with that certificate. And the way the SRX does that is you create a certificate ID, which is like a container, and all three things go inside. So we're going to make this certificate ID something obvious, like SRX0 cert. And then here we get to pick our size and type. So size, we're going to go with a standard 2048. You can make it bigger if that's what your organization needs. And then type, we're going to go with RSA. These are other types of certs that use other type of encryption algorithms. We're just sticking with RSA for this one. But like I said, if your organization needs these types of certs and has the ability to do them, feel free. So here we go, generating our RSA key pair. Now there it is. So there's basically a key pair in the SRX0 cert certificate ID container. That's basically what that's saying. So now let's use that key pair to generate our certificate signing request. Now this is actually one of the harder commands, right? Because here we're making that document we talked about earlier, where we're proposing all of the things that we want on our certificate. So there's a lot that goes in this command. So request security PKI, generate certificate request, certificate ID, right? We have to list where our key pair is located so that that public key gets put on this certificate request. Now we need to decide what the digest is going to be. That's the hashing algorithm. So we're going to say SHA-256, which I recommend don't use SHA-1. Use 256 or stronger. And then we need to do the subject. Okay. So this is that list of distinguished names, that list of strings I talked about, where we're going to say this is who we are, and this is what the CA's got to validate, right? So let's get that configured. Because our CA, is in Hawaii, we're going to do something similar. So we're going to say, oh, and you got to use these quotes right here. So open quote, we're going to say the common name, we'll just make it SRX.node9.lab. We're basically going to pretend that, we own node9.lab as a URL. And since the CA is at ca.node9.lab, and if you remember the CRL was at pki.node9.lab, so we're just going to say that this is SRX0 at, .node9.lab. So that's going to be our common name. Our organizational unit is going to be lab, kind of like a division of a company or something, or of a business. Our organization or company will be node9. And notice how I'm allowed to put in spaces. Our locality, we'll say, is the island of Oahu. Our state will be Hawaii, and our country will be US. So you don't have to have any of this stuff. The only one you have to have is a common name, but I'm just trying to make it interesting and kind of show you what you can do and how it works. Now there's the one final thing. I can't submit this. If I submit this, it's going to give me an error. And that's because, do you remember the subject alternative name that I talked about? So for whatever reason, Juniper SRX requires you to have something in the subject alternative name. And it can either be the domain name, meaning the FQDN, an email address, an IPv4 address, or an IPv6 address. So it's a little redundant, but just to make it simple, I'm going to go with the domain name, and I'm going to make it this name we have right here, which is our common name, which would make sense if this was like real and that was actually our real, FQDN, then this would make total sense that you would do your certificate this way. So here we go. Here's the certificate signing request right here. And you can see it's also in that base 64 format. And then here's that fingerprint. So now you can kind of get a better example of how these fingerprints are being used. This is the fingerprint before I moved it over to the CA, before a bad actor has had a chance to tamper with this, right? So once I move this over to the CA, then theoretically I would, on the CA, when I import it, I would just check this fingerprint and make sure, that it hasn't been tampered with and that there's no problems. And you know what? I forgot to export this to a file. So hang on. Let me clear out this real quick. Clear security PKI certificate request. Certificate ID. I'm just going to clear out this request real quick. And I'm going to do it again. I'm just hitting up arrow, all the same information, but I actually want to post it to a file, and we're going to put it in the PKI directory. And we'll call it SRX0.certificate signing request. So now it's not only being printed to screen, but it's going in my little directory right here, my PKI directory. And now I'm going to move it over to the CA off screen, and I'm going to get this signed. So stand by. I'm just moving this over off screen, and I'm going to get this signed. All right, I generated the cert, and it's now waiting for pickup at an HTTP. It says at the same HTTP URL that we used for this. So it's going to be file copy. It's going to be the same URL that we picked up the CA cert at. It's just going to be called SRX0 cert. And we're going to put it in the same spot on our local file system. Now look at this. Now you're starting to see all the pieces that going into PKI, right? We have the CA cert. Then we generated our certificate signing request that we sent to the CA. It got signed, and now it came back as this cert. So now we have two certs, the CA cert and then our device cert. So now let's get this loaded into our certificate system. So request security PKI. We're going to say local certificate load against that same certificate ID that our key pair is in and our CSR is in. So all three will be in the same container here. And we're going to say file name, and here's where we have to reference the file that we just copied over. And now it's loaded successfully. So again, this means that it already checked the cert. It made sure that it's within its validity period. It made sure that it's not revoked on the revocation list. Let's look and see what it looks like. So it looks a lot like the CA cert, right? But there's a couple of differences. Obviously, it has a different serial number. You can see here the issuer is different than the subject because it was issued by the CA, but the subject or who the cert belongs to is SRX0. Here's that subject string that we created. And here you can see the subject alternative name where we put the FQDN in because the SRX doesn't want it empty. And you can see this cert is only valid for a year. The CA cert was valid for 10 years. That's pretty normal. Although normally I guess a device cert would be good for like 3 years. And then here's our public key. Here's our hashing algorithm. Here's the CRL URL. And you can see this one actually has some additional information that the CA put on it that I did, which is it says the use for this key is IPSec tunnel. If you remember when we looked at the CA, it said use for this key, CA verification and signing. And then here's the unencrypted fingerprint. So at this point, all of our PKIs are loaded. We have the CA cert, we have the CRL loaded, and we have the device cert. So things are looking good. CA cert, CRL, device cert. All three of them are loaded. Everything looks good, no errors. So now we can start configuring the IKE and then the IPSec, right? We can move on to the next step in our little process here on the right. All right, so let's get started. So we're going to go back in config mode, set security IKE. We need to do our proposal first, and we'll name it something obvious like IKE proposal. And we'll first set our Diffie-Hellman group. We're going to go with group 14, which is a 2048-bit key. Then we're going to set our encryption algorithm. That's the algorithm that we're going to use to encrypt the IKE tunnel with once we get our Diffie-Hellman derived key. So we're going to go with AS256, which is what I recommend. And then here we're going to go with authentication method. Now, in the previous video, we did pre-shared keys. Here we're going to do RSA signatures because we have an RSA style certificate. So that's what we're going to use for authentication. And then the authentication algorithm, right, the hashing algorithm, we're going to go with SHA-256. And then we're going to set the lifetime. And we're going to do the full maximum time, which is 86,400 seconds or 24 hours. All right, so the IKE proposal is done. Now we're going to do the IKE policy, which needs to reference the proposal. Oop, let's name it something like IKE poly. And we'll reference the proposals we configured, which was IKE prop. And then the other thing we need with our IKE policy is, now when you do pre-shared key, this is where you define the pre-shared key. But we didn't. We did certificates, right? So here's we need to define what certificate we're going to offer so that the other side can authenticate us. And here's where we reference that SRX0 cert container, which has our key pair and our cert in it. All right, now our policy is done. So let's get started on the gateway. So now we're doing set security IKE gateway. and we'll just name the gateway SRX1 because that's where that's the neighbor, the peer we're talking with. So let's reference our IKE policy we just created. Let's set in the address. And if you're like me, you probably already forgot the address, so let's look back. The address is 43.164.20.254. All right, let me get that going here. Address, and get that pasted in. All right, so we got our address of who we're talking to here. Now we need to configure the external interface. This is the internet interface where the IKE tunnel and IPSec tunnel is going to anchor. Then let's set the version. We want v2 only. And now here is where it differs from where the pre-share key video went. With pre-share key, we didn't set the IKE ID, and so it defaulted to the IP address, namely the IP address on this gig 000 interface, because that's where the IKE tunnel is anchoring. So that's what our IKE ID defaulted to because we didn't set it. With certificates, your IKE ID has to be in your cert. Your IKE ID has to be a value that is findable in the cert. So if we don't set the IKE ID, we're actually going to fail authentication because our IKE ID will be our external IP address, but that external IP address wasn't put in the cert, which I did on purpose. And in some cases, your IP address might change, right? So that might not be the best thing to use as your IKE ID anyway. So in this case, we're going to use something from the cert. So let's configure that. So we're going to say local identity. And here's where we get to pick what we use for our local identity. This is the default, the IPv4 address of the exiting interface, external interface. We're going to pick distinguished name. Now what this means is we're going to take the entire string of that cert. So if you remember when we looked at our cert, local certificate, this right here, this entire string is called the subject. It's a list of all your distinguished names. Each one of these is called a different distinguished name. When we set the local identity to distinguished name, it's going to tell the other side, use this entire list to as our IKE identity. And then that way, so basically our IKE identity will be this entire subject list or string. So that's what we're going to set. And it's going to allow the other side to kind of look through this list and pick and choose what it wants to use to determine if we're the right peer that it wants to establish a VPN with. And we're going to do the same in reverse. So that's going to be our local identity. But when we are looking at SRX1, we're going to look for a certain thing in the remote identity. So we're also going to do distinguished name. But we're not going to leave it at that. We're going to say container, which means we're going to look at a specific distinguished name, and we get to pick what we look at. So what we're going to look at is the common name, and we're going to want that common name to look just like ours, but we're going to want it to say SRX1, right? So now, if we just look at this real quick, so we're going to offer up the entire subject list of our cert up to the other side. But when the other side offers their distinguished name to us, we're going to specifically look at the container called the common name, and we're going to make sure that that says SRX1.node9.lab. So this is one way of doing it. You can actually look at multiple different containers or distinguished names and just, to try to discriminate if this is the peer you want to do an IPSec VPN with, but we're just going to keep it simple. The other thing I want to do in this video is I actually want to set up dead peer detection. So set security IKE gateway SRX1. We're going to do dead peer detection. We're going to say probe idle tunnel. We're going to say interval. Let's send them every 5 seconds. Now, every 5 seconds, we're going to send one. And then the threshold, we're going to say 2. So that means every 5 seconds we'll send one. And we're allowed, it will retransmit 2 times. So basically this will be a 15-second dead timer is what you're looking at here. Because we're going to send one, wait 5 seconds, then we'll send one, wait 5 seconds, and then we'll send one more and wait 5 seconds, 15 seconds. And if we don't get a response within those 15 seconds from those 3 that we sent, the first one and then this threshold of 2 for 2 retransmissions, then IKE will think that there's something wrong and it will clear the IKE and IPSec and reestablish. All right, so we are now done with IKE. We have our Dead Peer Detection, we have our identity set up, we have our policy, our proposal, everything looks good here. So let's go ahead and move on to the IPSec. Set security IPSec proposal. And we're going to do protocol, let's name it IPSec proposal. We'll do protocol encapsulated security payload. We'll say encryption algorithm AES 256. For authentication algorithm, we're going to go with HMAC SHA 256. SHA-256. And for lifetime, we're going to go with, let's go with 8 hours like we've done in the past, 28,800 seconds. All right, so our IPSec proposals is done. Let's go to the policy, IPSec poly. And we're going to enable perfect reporting secrecy. If you recall, that's where when it's time to rekey the IPSec tunnel, we're going to rerun Diffie-Hellman on the IKE tunnel. And that way, if we have any bad actors that have hacked our IKE tunnel, they'll get flushed out because Diffie-Hellman will be rerun, we'll rekey the IKE tunnel, and the bad actor will be kicked out of the IKE tunnel. So we'll rerun Diffie-Hellman as group 14. And then our proposals, we're just going to reference the IPSec proposals we just made. All right, so now we have the IPSec proposals and policy. Now it's time to create the VPN. And if you recall, we're doing 2 IPSec SAs. So we actually need 2 VPN. So let's look at what that looks like. Set security IPSec VPN. We're going to name the first one SRX1_21 because it's going to be tunnel 21. So that just kind of makes sense. And first do the bind interface. So we're going to bind this to tunnel 0.21. Next, we're going to set the DF bit to copy. Next, we're going to reference the IKE gateway, which we called SRX1. So that ties IKE to IPSec. Next, we need to do our IPSec policy that we just created. And now right here is where we do the IKE Proxy Identity, also known as traffic selectors. So here's where we have to color or make a unique local and remote proxy identity that's going to be different from the second IPSec VPN tunnel we make, IPSec SA that we make. So the command is proxy identity and then local, and I'm going to make the local 1.1.1/32, and I'm going to make the remote 1.1.1.1/32. Now in a policy-based VPN, this would not work, right? Because in a policy-based VPN, you can't have traffic coming from 1.1.1 going to 1.1.1. Why would it even route out this interface, right? It wouldn't. But the reason why it works for route-based is because this is not being used as a decision whether something should be encrypted. It's just being used to uniquely identify this VPN from a second VPN we're about to create. So this proxy identity, this traffic selectors, is going to be negotiated with the other side so it knows that this VPN is different from another VPN we're about to create. But beyond that, it doesn't have any bearing. So let's create our second VPN, and we're going to call that SRX1 121. We're going to bind that to secure tunnel 121. And we're going to say DF bit copy. We're going to say IKE gateway SRX1. So do you see how I'm making a second IPSec VPN, but it's going to share the same parent IKE gateway. So we'll have one IKE encrypted tunnel, but we're going to have 2 IPSec VPN tunnels, 2 IPSec SAs. All right, next I need to set the proxy identity, and here's where it's got to be different. So I'm going to say 2.2.2.2/32 and 2.2.2.2/32. Now again, these numbers can be anything. I could have made this 2.2.2, I could have made the remote 3.3.3, but if I would have done that, then the other side would have to have a local of 3.3.3 and a remote of 2.2. You see how that works? So it's just easier if you just make the local and the remote the same number. That way when you configure the other side, it's the same number and you don't have to invert them. And also you could set the service here to whatever protocol but again, it just doesn't matter, so I just don't set it, which is default any. So because I'm not setting the proxy identity service, which is the protocol, it's just defaulting to any. So it just doesn't need to be set. So here's what it looks like. We have two IPSec VPNs. They're sharing the same IKE gateway, but they have separate proxy identities. And this is going to help the SRX on both sides to understand that these are separate VPNs, and they're going to bind to separate tunnel interfaces. And wait a minute, did I forget something here? It looks like on this one I forgot something. Good catch, guys, good catch. So let me get the IPSec policy set too. All right, so now both IPSec VPNs are configured. Let's configure the tunnels, right? So set interface secure tunnel 21, description SRX1. We'll say family INET MTU 1400 so that we don't have to worry about the overhead. Oh, and then we need to set the address. And if you remember from the drawing, it's going to be 172.16.21.0 on this side. And so we can copy all this same stuff for tunnel 121, right? And even the IP address is going to be similar. The difference is going to be 121 in the third octet. All right, so now our interfaces are set up. So let's configure the security zones. So show security zones. We need to get our tunnel interfaces in the corporate security zone. So secure tunnel 21 and secure tunnel 121. All right, and then we also need to, final step, run OSPF, right? So set protocol OSPF area 0 interface loopback, run it in passive, suppress the hellos, and then we'll run it on 21 and 121. So there we have it. This should be all the commands we need to make this work. So let's go ahead and commit those. And we'll very quickly, because I know probably most of you see my last video, so we'll just very quickly see what this looks like. It might take a second for IKE to get going here. There we go. So now IKE is trying to talk to the other side, right? It's not responding. The other side is not responding. That's why I responded to cookie is all zeros. But you can see we're trying to use RSA signatures, IKE v2, and here's our output packets. So we've only sent that one unencrypted init packet. One thing we forgot to do, and we probably should, is we probably should ping the other SRX and make sure it's reachable through the internet. So let's see if it is. Okay, yeah, it is. So we have the connectivity across the internet, but we just got to get that other side configured. One last thing, let's look at the show security IPSec inactive tunnels. So remember what I said, how if you have an IPSec tunnel configured, but it's not up, you're not going to see it under security associations, right? Because IKE is down, therefore IPSec hasn't spawned. But there's this really cool command in active tunnels that lets you see what tunnels are supposed to be up but are down. And here it gives you the reason. So it says, no response from peer, negotiation failed. So this is kind of cool how this works. Yeah, so anyway, we know we got the other side to configure, so let's go ahead and jump to the other side and get that configured. So here we are on SRX1, and we have all the same things we need to check. This one we're going to go a lot faster because you guys know what we're doing here. So check the flow mode. Yep, we're flow-based. Good to go. Let's check the interfaces. Okay, we got our internet interface. Yep, loopback interface. Check the routes. Yep, our loopbacks.21, just like the drawing said. Our internet interface is right here, which is good. And we already know we have internet reachability to SRX0 because that ping worked. And here's our default route. So everything looks good there. Let's check our security zones. Yep, we're allowing IKE to come through. Super important. We're allowing pings, of course, because the ping worked. And here's our corporate zone with our loopback 0 in it. This is where we're going to put the tunnel interfaces. And finally, let's check the policies and make sure we're allowing corporate to corporate traffic. So from corporate to corporate, so intra-zone, intra-corporate zone traffic is going to be permit any, match any, destination any, application, which just means protocol any, and then permit. So we're good there. So now let's check the date, right? Because we're dealing with certificates. So let's check our time here. So yes, it is 1856 UTC. That is the correct time. All right, so let's make sure we can ping DNS from this box, which the fake lab DNS server is this IP right here? Yes, we can. So we're going to need to configure that DNS as a name server for this is so we can resolve the URL so that we can download the CRL. And also we need to configure the container. You have to do this step first. You have to configure the container to put the CA cert in. So set security PKI CA profile. We'll also call this one CA prof. And then we got to give it an identity. Doesn't really matter. We're just going to call it CA cert. All right, so let's commit that. And just for fun, I'll show you the URL where the CRL is located is pki.node9.lab. And you can see that it was able to DNS resolve that to 255.1, which is just the lab server where I have like all the certs sitting on. All right, so now let's begin getting our PKI squared away. So first we need to do a file copy. Oh wait, hold on. Let's do a file list and make sure I have my PKI folder set up just to stay organized. And here you can see I forgot to delete out some of these from a previous video, so let me just clear those out because those certs are actually revoked. So I'm just gonna clear out all the files in that directory. There we go, because those are all bad files, they're all revoked. All right, so let's do a file copy, HTTP, and we'll get the CA cert. And we'll put it in our PKI folder. All right, so we got the CA cert there. There it is. So now let's load it into our PKI. So our container, so we're going to say request security PKI CA certificate load into the CA profile called CA profile. And we're going to pull it from the file that we just got here, which is PKI CA cert. And yep, that's the same thumbprint that we had on the other box. That is the correct fingerprint thumbprint, so yes. And it loaded successfully, so all the validation checks. So we'll just quickly look at the cert. Oop. Here it is. It's the same cert we had on SRX0, so no surprises here at all. You can see the use for this key is CRL signing and certificate signing. Speaking of CRLs, let's look at that. Yep, we automatically downloaded the CRLs, the same CRL we saw on SRX0 with the 3 revoked serial numbers. All right, so now what we need to do is generate our own key pair, right? Now it's time to get our own certificate. So we'll say request security PKI generate key pair. And the certificate ID, remember, which is just the container we're going to put it in, is going to be called SRX1 cert. And the size is going to be 2048. And the type is going to be RSA, because that's the type of cert. Oh, see, I forgot to clear out the keys I was using from a previous thing. So if you need to clear out your PKIs from anything previous, you can say clear security PKI. And this is where I need to say key pair, good ID, SRX1. Oh, and I need to clear out the cert. So I just have some stuff I didn't clear out here. So clear out certificate request, clear out local certificates, and clear out key pairs. All right, there we go. So everything's cleared out. Sorry about that, folks. So that was just a lingering container that had a key pair and a certificate signing request and a certificate from a previous video. So here we go. We're going to just do the same command as before, where we're requesting to generate our fresh key pair in the container SRX1 cert. And there we have it. So now we have the container and we have the key pair inside. So now we need to request security PKI generate certificate signing request. And this one we need to reference the same certificate ID, SRX1 cert, because that's where the key pair is located. We're going to do the digest of SHA-256. And here's where we get the ugly subject we got to write. So we're going to do common name equals SRX1.node9.lab. And then the OU, it's going to be lab. The organization is going to be, oh my goodness, terrible at typing. node 9, location, Oahu, state will be Hawaii, country will be US. So now we have our string, and if you recall, this will get rejected because we have to put something in the subject alternative name. So we're going to say domain name, and we'll just put our FQD, our fake FQDN in there, SRX1.node9.lab. All right, so here's our certificate sign request, and just like last time, I forgot to output it to a file. So hang on one second. Let me clear that out, and we'll regenerate it, and then we'll have it go to var temp PKI SRX1 dot certificate signing request. So we're just regenerating the same exact cert, but I'm sending it to a file. You can even see the fingerprint is the same. All right, so now I'm going to take this, and off screen I'm going to get this over to the CA and get it signed. All right, folks, I got the certificate signed by the CA, and now we're ready to pick it up. So let's go ahead and copy it. Oop. And it's just going to be at the same location where we picked up the CA cert. It'll be called SRX1.cert, and we're going to load it in the same PKI folder that we have. All right, so now we have it. So now let's get that cert loaded into our PKI container, which is called SRX1. Oops. We gotta say load first. Then we say certificate ID, SRX1 cert. And we also need to reference the file name here. Oh, it's under PKI. All right, cert loaded successfully. We'll quickly look at it. There's no surprises here. It's signed by the CA is the issuer, the signer is the CA, the subject is SRX1. Here you can see our subject string that we made, and here's our SAN that we populated with the SRX1 FQDN. You can see it's good for 1 year, and yep, everything is like expected. Use for this key is IPSec tunnel. So everything is going good here. All right, folks, so now that we have the SRX1 certificate loaded, and you can see the details, everything checks out here. Now we're ready to configure the IKE. So this is just where I'm going to do a bunch of copying from SRX0 because, we get it, we understand the configs. Now I'm just going to copy it over and make some minor changes. So let's kind of do that now. So back on SRX1, we'll do show security IKE. And look at all these wonderful IKE settings. So the only things I'm going to change, I'm going to copy all this over. I'm going to change the local certificate needs to say SRX1 cert, and the address needs to be SRX0's address. And that way we can connect to SRX0 from SRX1. And then of course I'll rename this to SRX0 as well. So let me go ahead and do that now. Just copy all this over. So I got it all copied and changed. So here I'm going to paste it in on SRX1, and I'll show you what we look like here. So now the gateway is called SRX0. It's pointed to the SRX0 IP, and the IKE policy is referencing our local SRX1 cert. And you can also see we're going to be checking the remote identity. We're expecting that the common name is going to be SRX0.node9.lab. So let's do the same thing with IPSec. So again, off screen, I'm just going to copy all this. And what's nice, since I use the same local and remote proxy identity, I won't have to invert these. Those can just copy straight over. The only thing I'll need to change is this SRX1 to SRX0. Everything else should be able to remain the same. Oh, and the gateway I need to change to SRX0. So let me get these copied over. All right, let me get this pasted in. And let's look at what I copied over. So we got the proposal, the policy, the VPNs, both of them. And we're referencing our gateway of SRX0, and we have the same proxy identity, so everything checks out there. All right, so now let's copy over the tunnel configs and the zones and the OSPF. So we'll say show security, not security, show interface tunnel. And let's get this copied over. And we'll just need to change the IP address and the description. All right, so on SRX1, we have the interfaces going to SRX0, and I update the IP addresses to .1 for each tunnel. Now let's look at the security zones. We need to add both tunnel interfaces to the corporate security zone, so we'll paste that in. And then finally, let's look at our protocols, because we're only running OSPF. So let's get that copied over. So now we have everything copied over that we need. We have all of our IKE proposal policy gateway, all of our IPSec proposal policy and both VPNs, and we have our security zone updated, and we have our tunnel created, both tunnels, we're doing 2 of them, and we have our OSPF configured. So let's get that committed. We're almost done, so let's take a look and see how we look, eh? So IKE hasn't started yet. Oh, there it goes. So you saw it was down for a second because it was still going through the process, but you could tell we were on the right track, right? Because we had our responder cookie. So at this point, both the init packets had been exchanged, but the authentication process hadn't completed yet. So it was still considered like a state of down, you know, because we hadn't properly authenticated each other. But we did see the other person's init packet at least. But the authentication must have been successful because we're up right here. So let's see what the detail looks like. All right, you can see the authentication method is RSA signatures. IKE, we know we use UDP port 500, so no surprises here. Look at the peer IKE ID. Remember how I said by default it's the IP address, and that's what we saw in the PKI, or sorry, the pre-shared key video. But in this video, you can see that the peer IKE ID is this long string, which is the subject that comes off the certificate. Here's all of our IKE proposals. You can see there's a lot more IKE traffic because of these keep alives we're sending back and forth to each other. These are you theirs. So if I just update this command, we're already up to 13. So I'm not recommending that you set the IKE dead peer detection to those low values, but I kind of wanted you to see evidence that it's working. Remember, we set it to send one every 5 seconds. So every 5 seconds, we're going to see one in both directions. And actually, both sides are sending one every 5 seconds. So every 5 seconds, we're going to see 2 in both directions, because you send one, are you there? And the other side responds, yes, I'm here. And since both sides are doing that, you see where this is. So it's actually going to be pretty noisy. You probably wouldn't want the timer that low. But then again, in a real world IPSec VPN, there would be so much IPSec traffic that it would never send them. Because remember, it only sends it if it goes 5 seconds and it sees no IPSec traffic. And since the only thing on our tunnels right now is OSPF, sending a hello every 10 seconds, you see what I'm saying? That's why the IKE keep alives keep sending, because the OSPF is just default timer. So our tunnels aren't noisy enough to suppress the dead peer keep alive are you there messages. So anyway, you see that our local identity and our remote identity. So both of us are sending that the subject, the list of distinguished names, to each other to be authenticated. All right, so let's look at the IPSec. So here you can see we have 2 child IPSec VPNs, 2 SAs, and you can see our proposals here that were accepted. Now the details for this is pretty ugly, but we'll look at them. So let's see. Here's the VPN, or the IPSec SA, that corresponds to the 121 tunnel, and you can see that it's where is it? Here it is. It's bound to the 121 tunnel. And then you can see the local and remote proxy identity or traffic selector, any protocol, but local and destination of 2.2.2.2. Again, it has no bearing. It's just helping it to discern that this is different from the other IPSec VPN. just a bunch of the settings that we had configured. Here you can see encapsulated security payload and all the proposals we configured. And then way down here you see the other VPN, which is 21, bound to interface 21, using proxy identities 1.1.1.1 on both sides. So there you have it. So now let's take a look and see. Obviously our tunnel interfaces are up, but what is our OSPF doing? So yep, our OSPF is up on both tunnels, full, and they've been up for about 4 minutes. The OSPF knows that these tunnels are going to the same router because look, it knows even though the peer IP is different, it can see that the OSPF route ID is the same. So, and now let's look at our routes. And here you have it. You can see not only our direct connected routes, but our OSPF learned loopback, which it knows through both tunnels, right? Makes sense. And so let's do our ping test here and see if pings work. Yes, they do. Yes, they do. So there you have it, folks, how to configure a route-based IPSec VPN with 2 IPSec SAs between 2 Juniper SRXs using PKI certificates for authentication. Do me a favor and like the video if you found it helpful, and subscribe if you're interested in seeing more. Thanks for watching.